In this lesson, we'll look at the EASA policy that determines the amount of fuel on board the aeroplane prior to startup to complete a planned route from departure to destination. It is the commander's responsibility to ensure that there is sufficient fuel on board the aeroplane in accordance with the operational flight plan. We will see how the final fuel total is arrived at by breaking it down into segments, which will be described and built up in the form of a fuel policy diagram in the following scenes. Let us begin by looking at the total fuel in the aeroplane tanks prior to starting engines, which is described as the block or ramp fuel, comprising the sum of each of the individual fuel segment requirements. The first of the segments that makes up block ramp fuel is called the start or taxi fuel, which is a specified amount of fuel required to start up, taxi and hold if necessary, before lining up on the runway for takeoff. It will also include an amount used by the auxiliary power unit to provide necessary services prior to engine start. The next consideration is the make-up of trip fuel. The trip fuel includes the fuel used for takeoff, initial climb, including any standard instrument departure or SID, and continuing to the top of the climb. Also included is the fuel used in the cruise to the top of the descent point, and, from there, the fuel used in the descent and approach, including any standard terminal arrival procedure, or STAR. Finally, the trip fuel includes the amount used for approach and landing at the destination. The trip fuel, previously defined, has an addition which is known as contingency fuel. The contingency is built in to compensate for any unexpected deviations from the planned trip routing, cruising levels, or maybe encountering any unforecast unfavourable Met conditions. It also allows for any individual aeroplane's fuel consumption being different from standard. The increase is fixed at up to maximum of 5% of the calculated trip fuel. Having looked at the fuel required to get us to our destination, we must now look at preparing for the possibility of being unable to land due to unplanned situations. Should it be necessary for the aeroplane to divert to an alternate aerodrome, the required fuel is called alternate fuel. The alternate fuel allows for a missed approach at destination and the fuel to route to the alternate, taking into account any expected wind component. If the aeroplane flies from departure to destination and uses all of the contingency fuel, and has to carry out a missed approach at destination to fly to the alternate aerodrome, you can see that that would leave us with no fuel on arrival at the alternate. To avoid this situation, included in the total fuel is an amount called final reserve fuel. We therefore have a minimum landing fuel, and all being well normally, we should never land with less than final reserve. The reserve fuel for a turbojet consists of fuel used in 30 minutes at 1500 feet, flying at endurance speed in ISA conditions. For a piston-engined aeroplane, it is the fuel used in 45 minutes at endurance speed. The trip, contingency, alternate and final reserve fuel previously discussed cover most of the fuel requirements. However, there may be occasions when some additional amounts are needed to cover other eventualities. Take the case where an aeroplane is a long distance from an en route alternate and it suffers either an engine failure or, even worse, a pressurization failure, necessitating descent to a low altitude. Flying at the lower altitude will result in higher fuel consumption than planned. There will also be a case for taking additional fuel when the destination aerodrome is so isolated that no alternate is available, and so on this occasion an amount known as island holding is required. The necessary fuel carried to cater for the possibility of these occurrences is called additional fuel. Finally, in addition to satisfying the EASA minimum fuel requirements discussed, the aeroplane commander is allowed to add to the total if he decides that more is needed because of particular circumstances. The amount of fuel in this case is called extra fuel. On screen, you will now see all of the fuel segments that contribute to the total fuel on board the aeroplane prior to startup, which becomes the block ramp fuel. Having determined the amount of fuel required for the flight, it is now necessary to convert the mass to a volume, because the fuel operator works in US gallons, imperial gallons, or litres. In order to convert the mass, pounds or kilograms, to volume, gallons or litres, the specific gravity, Sg, must be known. The fuel operator will usually provide the actual specific gravity of the fuel, but if not, a standard one can be used, which can be found in the operations manual. This is a good moment to remind ourselves of the basic connection between density, volume and mass. Density is defined as mass per unit volume, and relative density or specific gravity is simply a comparison of the heaviness of one substance with that of water. On screen you can see that an imperial gallon of avgas, the fuel we use in piston engine aeroplanes, weighs 7.2 pounds force. Notice that weight is given in pounds force, but in mass and balance calculations we use mass. We now compare the weight of the fuel, 7.2 pounds force, to that of an equal volume of water which weighs 10 pounds force. To find the specific gravity, the weight of the fuel is divided by the weight of water, resulting in an Sg of 0.72. In order to help you with the conversions, you will see on screen a handy chart illustrating all the steps needed to change volume to mass and mass to volume. In the left-hand column, the fuel quantity is listed in US gallons, imperial gallons and litres, and in the right-hand column, mass is listed in pounds and kilograms. The necessary conversion factors are listed along the appropriate lines. To carry out a conversion using the arrows, multiply the box at the tail of the arrow by the conversion factor, and when moving against the arrow, divide the box at the arrowhead by the conversion factor. The following practical examples will guide you through conversions. We will work through two examples on screen using the chart. In example 1, convert 1,000 US gallons of Jet A1 aviation turbine fuel with a Sg of 0.83 into kilograms. To solve example 1, start by dividing 1,000 US gallons by 1.2. This becomes imperial gallons. Now multiply by 4.546 to bring it to litres. And finally, multiply by the Sg, 0.83, to reach a solution of 3,144 kilograms. Example 2 demonstrates going in the reverse direction, converting kilograms to US gallons. Using 1,000 kilograms, we will convert it to US gallons. First, multiply 1,000 kilograms by 2.205 to bring it to imperial pounds. Now divide by 10 and 0.83 respectively to obtain imperial gallons. And finally, multiply by 1.2 to reach a solution of 319 US gallons. Knowing how to make the conversions will stand you in good stead, especially when you get to constructing mass and balance tables later in the course. There are some basic conversions in CAP 696 in section 1, page 4, which will also help you. In this lesson, we have looked at the EASA policy for the planned minimum fuel load, which must be on the aeroplane prior to start-up for any flight. We saw that the requirements are broken down into segments, which, when totaled, constitute the ramp or block fuel. Because the fuel on the aeroplane is indicated by mass units and the uplift fuel is calculated in volume, we have learnt to do the necessary conversion by using a convenient chart, using worked examples. We can also use a more direct conversion choice from US gallons to litres using CAP 696.